All right, so one of the first things we're going to go through are the physical differences between these two things. So between pulley drives and sprocket systems, okay? Because we talked about the calculations all the same. Calculations are always the same. No matter if you're talking about gears, sprockets, or pulleys, all the calculations are the same. There's some physical differences, right? So, and I'll start you off with a couple and then we'll kind of build off of it. So, with a sprocket system, sprocket systems have teeth on them. So a pulley drive have no teeth. Because they have no teeth, or they have teeth, how do you think that impacts what happens? How do you think that what do you think happens? So you can make a pulley drive make other ones move even without teeth, but let's kind of build on that. Because it doesn't have any teeth, do you think it's allowed to slip? Yeah. So a pulley drive is allowed to slip. Now you might look at that as a bad thing. I might even look at it as a good thing. So if this can slip, what do you think this can't slip? So no slip. No slip on the sprocket. Why has it got no slip? Because it's got teeth on it. It's got interlocking teeth. So we don't want things to slip. If we're using a sprocket system, that's one of the things, one of the reasons why we don't want it to slip. What do you think in terms of material? What do you think they're made out of? So we'll do the easy one. So a sprocket system. The sprockets are made out of metal usually. What's the chain usually made out of? Also metal. So it's both metal. Metal gear, metal sprocket, metal chain. Now on a pulley drive, it's also, the pulley is usually metal. But how about like the belt? What do you think the belt's usually made out of? Yeah, so rubber. Rubber's usually what the connecting material is. All right? And, bless you. So because of a sprocket system is metal on metal, what do you think we have? What are some characteristics with metal on metal contact? What do you think we have to do maybe? Right, so we get an oil. We get an oil a sprocket system. Yeah, we have to lubricate that metal system. Because if you don't, they're going to grind each other and they're just going to completely wear each other out. Right? What do you think happens if you put oil on a pulley drive system? It's going to slip like crazy. That's going to be like a disaster. So no oil is going to be what we're looking for on a pulley drive. Think of noise. Metal on metal versus metal on rubber. Yeah, so metal on metal, so the sprocket system is loud or louder. Well, not loud. Loud. And I'm going to put not loud because we're not going to say it's quiet because it's still going to be kind of noisy. But we're going to say it's at least not as noisy. Which one do you think is more expensive? Yeah, so sprockets are probably going to be, more money. Pulley is going to be a little less money because it's not going to require as much metal. And the pulleys are going to be easier to make because they're not going to have any teeth, so it's less intricate of a design they have to make. So those are kind of the physical differences between them two. All right, so we all know when you ride like a bike, right? A bike has a sprocket system, right? Yeah. Right? So a bike has a sprocket system, right? Sprocket system has teeth on it. Why do you think it's important that a bike has a sprocket system and not a pulley system? Because we could make it, maybe we want it to be quieter when you ride. You could do that. So they're stronger. All right, they won't slip as easy. I don't know if you've ever ridden a bike that has a worn out chain, or your chain slips. If you're in like a cadence and you're riding along and all of a sudden your chain slips, it really throws you for like it's like whoa, right? And it kind of throws you off. It doesn't throw you off balance. You don't usually crash or anything like that, but it throws off your cadence. Which your cadence is like, how well you're pedaling, like the repetition of your pedaling. When that happens, it really throws you off. And if you're going up a hill and that happens, forget it. You've lost all your momentum, and now you're in trouble, right? Where might we use a pulley drive? Well, one place we use it is on the front of an engine. We have all these accessories on the front of an engine. So we have an alternator. Tagad Bernstein. Oh, okay. Awesome. Thanks. Bye. So, on the front of an engine, we have all these accessories. What are some of those accessories? Well, an alternator, which doesn't create electricity, but it converts spinning into electricity, kind of like a turbine, right? What else do we have? Well, we have a smog pump for emissions to make your exhaust cleaner when it comes out the tailpipe. We have a water pump to cool your engine. We have an AC compressor. So you have what? Yeah, so you have air conditioning, right? So a lot of times, all of those systems are driven by a pulley system. Why are they driven by a pulley system? Because are they necessarily important? Do they have to be perfectly aligned with each other? Like, if one slips a little bit, do you think it's going to affect the other ones? Is it going to matter, though? No, it's not going to matter, right? So if they slip, it's not a big deal. So they use a cheaper system, right? But the problem is on the inside of the motor, well, not really the problem, but on the inside of the motor, we use sprocket systems, because inside the motor, we already have oil, because oil's in the motor, and we have all these things that have to happen in time with each other. When this thing moves, then this thing has to move. And when those two things move, then this thing has to move. And all this stuff has to happen, right? And if one of those moves when it's not supposed to, essentially one of those slips, what do you think happens? Yeah, like that motor fails like big time, right? It like explodes. And when I say explodes, I don't mean like, Hollywood explosion. I just mean it stops working. You have to take your car to a mechanic and it's like a $3,000 bill, not just an easy fix, right? So we use sprocket systems on the inside of the motor, right? All right, so let's take a look at the equation stuff, and I'll show you how much they are the same. The math is all the same. So we have a sprocket system or a pulley system, really doesn't matter. We're going to say it's a sprocket system because those are teeth. 20 teeth on the left, 100 teeth on the right, so 20 teeth in, 100 teeth out. If I asked you for gear ratio, how would you do it? Somebody raise your hand and tell me how you would do it. So you would do N out over N in, so you would do 100 over 20 to get 5, right? Yeah. All right. Now, is that any different from gears? No. Right? The only difference in terms of physical is if this in spins clockwise, this out also spins clockwise. They spin in the same direction because that's just the way that they are linked together. So what if I said to you this thing is spinning at 200 RPM? I want to know how fast the out gear is spinning. You have two ways you can do it. Two ways. Two ways you can do it. So what do we have? Well, we have gear ratio, which we've already solved for is 5. We have speed in is 200. We want to know speed out. So do we have a formula that has speed in, speed out, and gear ratio? What's that formula? GR equals W in over W out. So GR is 5, speed in is 200, and speed out we don't know. Slide down here. So this is where people sometimes fall apart. And we've talked about this formula many times already. Many times. What people want to do is they want to do 5 times 200. Can't do that. They want to do 5 divided by 200. You can't do that. You can't touch the 200. You can't touch the numerator. You're not allowed. The only thing you can move is the denominator. And if you think back to what I've been doing, I've been telling you if you have your variable on the bottom and you have what I call a Lone Ranger over here, what can you do? You just switch them. Because that's all the math is going to have you do. You just flip them. So, W out equals 200 over 5. What do we get? So we get 40 RPM. So let's do ourselves a quick check. Do ourselves a quick check. And I'll scroll down. I'll scroll back down here in a second. Is this a bigger gear? Is this 100 a bigger gear? Yep. Yes. So it should be spinning slower or faster? It should be spinning slower because it's bigger, right? Bigger the gear, slower it spins. Is 40 slower than 200? Yes. So it checks out. So what's another way we could do it? Instead of doing that way, assuming that we didn't find gear ratio already. Well, we don't have torque, we don't have diameter. Could we do this? Right. We could do N out over N in equals speed in over speed out. Couldn't we? Because we have all 3 of those. Yes? So we have 100 over 20 equals 200 over X, essentially. Plug in what we know. So what are we going to do? What are we doing now? Yeah, we're going to cross multiply. So we get 200 times 20, 4,000 equals 100 W out. Then what? Divide by both sides by 100. And what do we get? Also 40 RPM, because either way works. Okay? Which way would I go? Well, if they were asking me for gear ratio first and then speed out, I would do the left-hand side. If they were asking me just for speed out, guess which one I'm going to do? I'm going to do the right-hand side. Why? Because it's a little faster. It's not super fast, but it's 1 step faster. Because I didn't have to find gear ratio individually by itself. Did we kind of find gear ratio already, though? Like in this right-hand formula, in this right-hand set, where's gear ratio represented? It's there. Right, so the 100 divided by the 20, that's the gear ratio. 100 divided by 20 is just 5. That's our gear ratio. We're just not solving for it in this case. Okay? All right, let me give you another one because you guys said diameter. So here's a sprocket system. Just to give you an idea, that is a component that people in the car industry would call it a timing chain. It goes on the front of an engine, usually inside the engine, but the front part of the engine. And what it does is it makes two rotating assemblies in sync with each other. So it makes the large crankshaft at the very bottom of the engine turn at the same, not the same rate, but at the same timing as what we call the camshaft, which is where the little one's going to go. Okay? So we have 12 teeth on the small gear. We don't know how many teeth on the big gear. Small gear is 2 inches in diameter. The big gear is 8 inches in diameter. And we need to find how many teeth. So what do we have? We've never done this problem before. You guys have never seen this picture before. So what do we have? What's one variable we have? So we have diameter out, which is 8. We have diameter in, which is 2. Okay? What else do we have? Right, we have N in as 12. We don't have N out, so we're going to put that as our unknown. So we have 4 variables. Do you have an equation that has all 4 of those in it that'll solve for one of them? Yeah. So we have a formula that's N out over N in equals D out over D in. At this point, we just plug and chug. You don't even need to look at the pictures anymore. So, N out, we don't know. N in is 12 equals 8 over 2. So what's 12 times 8? So 96 equals N out times 2. Divide both sides by 2. And we get N out is 48 teeth. So we have 48 teeth. Think of it this way. How much larger is the bigger gear versus the little gear in diameter? How much larger? How many times larger is the bigger gear? So it's 4 times the diameter, right? That means it has to have 4 times the amount of teeth on it. Small gear's got 12. It's got to have 4 times the amount of teeth. So 12 times 4 is 48. Okay? It's got to be 4 times the size. Okay? All right. We'll take a look at the last one. So you guys are familiar with that object, right? So we got a bicycle. Okay? Now, that's a mountain bike or some form of a mountain bike. Point is, it has changeable gears. All right? It's got low gears, being like 1, 2, and 3. And high gears, maybe they go up to 16, maybe they go up to 27, depending on the type of bike you have. Okay? The point is, all of those gears allow you to start off very easily, but also allow you to go very, very quickly. Okay? So let me ask you this. When you start riding a bike, when you just initially start moving, do you want more speed or do you want torque? So you need torque. So what you essentially telling me is you need more gear ratio. At the beginning, you need more gear ratio. And as you speed up, you want less gear ratio. Less gear ratio means you're going to have less torque, but you're going to have more speed. So when you're at the high gear, when you're at like 27th gear or whatever, your gear ratio is going to be very low, but your speed is going to be very high. And you'll see how that works here in a little bit. Okay? So, right, so at the beginning, it's easier to pedal when you're in first gear, but your feet are going really fast, and you're not really going anywhere. Right? But when you're at the high gear, your feet are moving pretty slow, but you're going really fast. Okay? So you're giving up speed to get torque, and then you're going to give up torque to get speed. Okay? So we'll do this 2 ways. So this is first gear. We'll say it's first gear. Okay? Now you're going to have to think about this, and I chose this problem specifically because I want you to think about it, okay? So, at the beginning, in first gear, do you want torque or do you want speed? We want torque, right? At the beginning, we want torque. Where does torque come from? Smaller gears or larger gears? Larger gears. Larger gears are going to give you more torque. Okay? So, that means you want a large gear at the back. Okay? So, we're going to say that this back gear has 50 teeth on it. So that back gear has 50 teeth on it. And let's say the front gear has let's say 20 teeth on it. What's my gear ratio? You're probably thinking, well, which one's my in, Mr. Bernstein? You haven't told us that. You're right, because it's a bike. I shouldn't have to tell you which ones you're in. Where do you apply your force? On the front sprocket or the back sprocket? At the front sprocket, where the pedals are, is where you apply your force. So the front is your in. So we're going to do N out over N in. What's my N out? 50 over 20. What do we get? So we get 2.5 is our gear ratio. That means what? That means for every one rotation of the back, your front has to spin 2.5 times. That's why your feet really go pretty quickly. Your feet are moving like crazy, but where are you not going? Yeah, you're not really going forward that much because your feet, because you've essentially taken a disadvantage. Your feet are speeding like crazy in order to get a lot of torque out of it, which allows you to move easier. So like the really small ones as in like first gear. So first gear on a mountain bike really isn't to get started. It's really to like go up a hill. So like a pretty steep hill. It's not really meant to kind of move, from a standstill. It's more used for when you're going up a hill kind of thing and you're trying to go slow, right? Because if you think of that like mountain biking, you ever been like real like mountain biking? It's like the terrain is pretty hectic and you can go up some pretty steep hills on a mountain bike. A 40% or a 40-degree incline is a pretty steep hill that you're not going to encounter on like a typical roadway kind of thing. So that's why they put those on there. So they're not really for normal riding. They're for mountain biking like type things. Good question. So let's change the problem. And instead of being in first gear now, let's be in 27th gear. So now 27th gear, and again, you've probably never noticed this. You probably will now if you have a bike. In 27th gear, or the highest gear, you're going to be on the big gear up front. So the big gear is going to be up front now. What do you think is in the back? Yeah, the small one. Probably, I don't know if you've ever noticed this, but the ones in the back, they go pretty big to really small. So instead of 20, we're going to say it's got 12 on it. Because they do get smaller than the ones in the front. So now, we're going to do N out over N in here, and we're going to get 12 over 50. What do we get? 2.24? 0.24. So we get a very low gear ratio. A very low gear ratio is going to give us a lot of speed. Don't believe me? For every one rotation of the little one, you're going to go a 0.24 rotations of the big one. So if that doesn't make sense to you, let's do it like this. For every 1 rotation of the big one, that's your speed in. Find me your speed out. For every 1 rotation of the front one, find me the speed out. Well, what do we have? So we have GR, right? You guys told me GR is 0.24, right? What else do we have? We have speed in, which is 1. I want to know speed out. So, bless you, 0.24 equals 1 over x, essentially. So we're going to do that switcheroo again. So we get x equals 1 divided by 0.24, which is? So 4.167, essentially RPM. So for every 1 rotation, your feet go. Your rear wheel spins 4.167 times. So you're speeding at that point.
Remember when our famous food quiz, we had to be very precise with what numbers we used?
Mm-hmm.
Is that the same with this? Like, if you still have a large number, do you want us to use the whole thing?
So my rule of thumb for you guys is you should not round till the very end. Okay? And a lot of you have calculators that are very capable of that, meaning you can like just scroll up and click a number and bring it down. I would highly suggest that you not round till the very end. For everything. For everything. That's my rule of thumb. Don't round till the very end. Okay? All right? Does that make sense? Okay? All right.